So today we will start off with your indicator diagrams. Okay, very important concept. We will be using it for the other topics as well. You check, this indicator diagrams are going to tell us everything, or not everything, but most of the things about your system. Okay, what is the system undergoing, okay, what conditions it is present, and what can happen to this system. Okay, so see, this indicator diagram, okay, to be more accurate, we have another name. We can call it PV indicator diagrams. Okay, PV indicator diagrams means pressure volume indicator diagrams. Okay, and they are nothing but just graphs. They are graphs which shows how the pressure of that system, okay, how does the pressure of the system changes with the volume. Okay, so that is what we are going to deal with. Okay, so the first diagram you can just check. Let me just show you here again. These diagrams means basically, this means they are graphs only. Okay, let me use this ink here. So see, so in the x-axis we are going to plot something called volume, and in the y-axis we are going to plot something called pressure. And let's say right now I have a system of particles, that means gases, enclosed in a piston, frictionless piston. Okay, and the piston is right now in this position because all these gases are pushing the piston. Okay, all these gases are green molecules that I'm trying to draw. They are pushing the piston. Okay, see all these green gas molecules that I've drawn. Okay, they are pushing the piston. That's why the piston is in such a level. And right now we have a volume, let's call it V1. That's the initial volume. The molecules are pushing the wall, so let's say the pressure right now is P1, and because of this, okay, let's also say the temperature of this particular gas is right now T1. Okay, so maybe some temperature, that is what we have right now. Okay, so Rikinti also have joined. Okay, so see, Rikinti, we just started. Okay, I'm just talking about something called PV indicator diagram. Okay, PV indicator diagram. So what are they? See, so right now you can check, since this is the volume axis, this means zero volume, right? Okay, no volume. Okay, this means, let's say, volume V1, and if I go to the right, I'm talking about bigger and bigger volumes. We're talking about more and more space occupied by the gas. So let's say we have another volume here, let's call it V2. Okay, so basically you're obviously right, your V2 is a greater volume compared to your V1, and right now this is the picture, this is the initial condition of the gas. Okay, initial condition of the gas. So now you know what, the pressure of the gas is P1 right now, so we will have to plot it in the pressure axis. You can check. So when the volume is V1, let's say the pressure of the gas is this much. Okay, we call it P1. Okay, this is what we have right now. Okay, and depending on, right, okay, whether the temperature can change or not, whether it's an isothermal or adiabatic process. Let me start with isothermal for the time being. Okay, let's just talk about isothermal, no problem with that. So if I start with isothermal process and I tell you that the gas is going to expand. Okay, so if I talk about isothermal process and the gas is going to expand, so my new picture is going to be this. Okay, we have this same cylinder, but now the gases, okay, now the gases are occupying more volume. So now the volume, I'm going to say it has reached how much volume, guys? V2. So volume has changed from V1 volume, now we have more volume, we got V2, right? And because it is isothermal, right, we are going to say that the pressure is now P2, and we know, right, we can obviously say that the pressure P2 will be smaller than pressure P1. P1 is smaller than P2. Volume V1 is smaller than V2. Okay, but pressure, okay, pressure P1 is less than P2. What does it mean? See, the volume has definitely increased because this is your expanded volume, this is more volume. Okay, so when the volume increases, the pressure is going to decrease. So your initial pressure is high, but your pressure at later time is going to be low. Okay, so how does this fall, right? So every graph, if you remember, will have an equation, and we also have an equation. Okay, we have PV equals to N into R into T, and check P1 V1, I can just call it some temperature. Then I can have P2 V2 equals to nRT. This can happen. Okay, this can be happening, right, because I told you it is an isothermal process. In an isothermal process, the pressure and the volume can change. The pressure and the volume can change, but the temperature does not change. Okay, so we still have these two equations that can work out, and if the volume increases, the pressure has to decrease. Okay, so how will I plot in the graph, or how will the graph look like? See, okay, this is your pressure P1, which is a initial greater pressure, and this is your pressure P2. Okay, don't worry, you'll get the graph what I'm trying to tell you. So when we plot the graph, it's going to happen like this. See, when the volume is V1, the pressure is P1, so my points will be somewhere here. Okay, it indicates that the gas had a volume of V1 and the pressure of P1. Okay, but when the gas has a different volume, look at this, I'm going to the right now. Okay, now the gas has a bigger volume. Now the pressure cannot be same, right? It is isothermal process, the pressure is going to fall. So the pressure will fall to a value called P2, and this is the one you can check. Okay, so this is a new state of the gas. I can call it volume is V2 and the new pressure is P2, and the whole graph in between is going to look like this. Okay, and I also have to show you an arrow in this direction, that this is the course of the reaction, right? This is how the reaction proceeds from low volume to a bigger volume. It is expansion. I think you're clear with this. Okay, the arrow, look at the arrow. Where is the arrow going, guys? It is going in the in the direction where the volume increases or the volume decreases. You can check that. No, this arrow is showing you that the arrow is going in the direction of increase of volume, okay, and decrease of pressure. It is not a straight line. Okay, it is not a straight line. Let's be clear with that also. It is going to be a curved line like that. Okay, but indicates that the pressure is falling. Okay, and the volume is increasing. So I am going to call it what, guys? Expansion. Okay, notice something. Say, if I tell you this is the volume called V3 here, then what is the pressure? You know, the pressure of this gas is around this much. So when the volume is this much, the pressure is going to be this much. Okay, and this is, I can just indicate it as P3. Okay, so this is another state of a gas, and like this we can have many state of the gas. Okay, so let me just quickly draw another graph very quickly. Just check, not a very difficult thing that I've talked. Okay, see, so even if I have a volume here, volume graph, and this is the pressure axis, this is volume V1, this is volume V2. Definitely volume V2 is greater than volume V1, and I have, let's say, another two notes, or not notes, but let's say points for pressure P1 and P2. You can understand which one is great and which one is small. P1 is large, P2 is small. Check. Okay, when the volume is V2, it is here this much, and when the volume is V1, the pressure is this much. Okay, but now if I draw the graph like this, see guys, if I draw a graph which look like this, what does it mean, guys? Can you tell me what is it indicating? The gas is undergoing expansion or compression?
Compression.
This is compression. Why? Because my arrow is going in such a direction that it indicates increase of volume or decrease of volume.
Decrease of volume.
Decrease
Decrease
of
of volume. So decrease of volume is compression. Okay, and whenever you compress a gas, it's like this, right? The piston is going to be not here, the piston will reach somewhere here. So now you tell me, okay, the gases will apply pressure or will apply more pressure?
more pressure.
Because now, yeah,
More
because
pressure.
because now the gases have been compressed and made to stay in this small volume. Now they are going to go and hit the walls more often, and we are going to get more pressure. Okay, so basically it's just indicating what is happening, right? Okay, and I can also mention the temperature for the entire graph. Okay, I can do it. I can just say temperature is T. So I think PV indicator diagram is not very difficult thing. For the time being, I think we are doing fine. Okay, I think we can proceed. Okay, with this thing, not a difficult topic. Okay, let's really start with isothermal change. Okay, see, last time I may not have talked properly, but today we really need to do it properly. This is what we are going to do. We're also going to study adiabatic change. Okay, properly we have to do it. Okay, these formulas we have to learn it for numericals. That's what we need to do. Then we can at least go for a work done in isothermal expansion. Okay, so see, let's be clear. Okay, see, isothermal change. Okay, isothermal change, I told you at the beginning, pressure and volume can change in the system, yes, okay, but if the temperature of the system does not change, then such a change we are going to call it what change, guys? We are going to call it isothermal change. Thermal, you can already understand, comes from the word temperature. Okay, so temperature does not change. Okay, now what can happen? Okay, the heat can be exchanged, because heat and temperature are not same. Okay, temperature can change, sorry, cannot change, but heat can change. Heat can be exchanged by the system or by the gas with its surroundings. Okay, I'll give you an example. Check, then you think and tell me whether it makes sense or not. Okay, see, oops, give me 1 second. See, okay, this is a container. Let me draw it properly. If you understand this, adiabatic will be again easy. Okay, see, so this is the gas that I'm trying to draw, This is the piston right now, okay. Right now the volume of the gas is V1, pressure of the gas is P1, and let's say the temperature right now of this gas is T, okay. Now see, what I'm trying to tell you is that just now I told you, okay, can heat enter the system? Yes, heat can enter the system. Heat can also what, guys? Okay, my screen has gone, no? What happened? You cannot see my screen, no? Oops.
Yes, sir.
1 second, huh? Can you see now? It's back. Okay, so heat can enter, don't forget, okay, heat can enter the system or heat can leave the system, okay. Heat is energy, don't forget that, okay. So I have that heat can enter or leave the system, okay. So this can happen, this can happen, okay. Now see, suppose I tell you that the piston has reached here. Now you tell me, okay, now you tell me that, oops, now you tell me, okay, what is this? I will call it, will I call it expansion or compression right now? Can I call it expansion?
Expansion.
Yes, sir.
I can call it expansion, okay. Now think and tell me, okay, if heat has entered, let's call it Q, okay, for that heat has entered the system, heat is energy, okay. So do you agree with me that the piston has reached here because heat has entered, and because of heat, right, the molecules are using that heat to go and push the what? Piston. Do you agree
Piston.
with this? Think again, okay. Because we have heated the gas, okay, because we have heated the gas, the volume has changed. The volume now is not V1, now the volume is what? Now the volume is V2, okay. Did the gas, okay, push the piston or not? Yes, the gas could push the piston. And why it may happen so is because the gas is gaining what? Heat, or let's say energy to do that, okay. So when the gases are pushing the piston, okay, you tell me, will the pressure fall or not fall? Right now, in this case, will the pressure fall or not? That's the first thing. Pressure will become what, guys? Pressure will become P2. Will it fall or not fall? What do you think? It may fall or not?
It will fall.
It may fall, yes, the pressure may fall. Why? Because volume increases, pressure has to fall, okay. But do you agree with me that the temperature may not fall or not? Temperature falls or does not fall?
Does not
May
fall.
not fall.
May not fall. Why? Because if okay, if there was no heat, coming into the system, and the gases are what? Pushing the piston, okay, and the gases are pushing the piston. Now you tell me, the energy of this gas will remain the same or the energy of this gas will decrease?
Decrease.
Decrease.
Energy of the
Decrease.
gas has to what? Decrease, okay. Why? Because there's no energy and no help coming from outside. The gas is pushing the piston. Why? Because the gas is using its own internal energy, okay. The gas is using its own internal energy, and that's why, you know what, the energy of the gas decreases. And what does it mean the energy of a gas decreases? Temperature has to be same or temperature falls?
False.
Temperature
False.
falls. When the gas has to use its own energy, then the temperature will fall. But in this case, which I showed you just now, energy was entering the system, and that's why temperature of the gas has to fall or may not fall.
May not fall.
Yeah, the temperature may not fall. That means the temperature may not change. There's no change of temperature. Why? Because gas is really getting energy from outside to do this work, and the gas will not lose its internal energy, okay. Such process, we are going to call it what, guys? We are going to call it, right now I'm going to call it expansion, or I can call it adiabatic expansion, guys. Sorry, isothermal expansion, or it is a compression. First of all, it is what we have to call it, isothermal expansion. Okay, so
Expansion.
you tell me, okay, very quickly, what is isothermal expansion? Tell me, guys. It is nothing but increase of what? Or expansion of a
Gas.
Of a
gas,
gas.
right? And in such a process, obviously the pressure falls or doesn't fall? Pressure falls.
Pressure.
Pressure
Pressure
falls. Okay, because the walls are going far, okay, the pressure falls, but the temperature falls or does not fall?
Remains
Does
constant.
Doesn't
the
fall.
temperature may remain constant, and if the temperature is remaining constant, what does it mean? Heat is entering the system or not entering the system from outside?
Entering the
It is
system.
The
entering.
heat is entering the system from outside. That's why the temperature does not fall. Okay. Now, pressure falls. Yes, is correct. But do you think the pressure falls or pressure falls slowly? What kind of
Slowly.
pressure? Pressure
Slowly.
falls. Pressure falls. Okay, but it falls very, very slowly, not very fast. It's not just going to lose all the pressure very quickly. Why? Because there's energy which is going to sustain this pressure. Okay, so let me just show you what else we need to do for isothermal expansion. Okay, check. See, I'm going to write something which you are clear. I'm going to write PV equals to nRT, which is ideal gas equation or a perfect gas equation. Check whether it makes sense or not. Okay, say I'm going to use two states, that is P1 V1 equals to N into R into T. I'm also going to write P2 V2 equals to nRT. Agreed? Okay, why? Because I told you temperature does not change, the temperature is a constant. Okay, so notice both of them, the right hand side. Do you think the right hand side of both the equations are different or same?
Same.
Same, constant. Okay, right hand side is constant. Okay, because you can check, R is a constant, N is a constant. In this process, T is also a constant. So if T is constant, what you're going to write? PV equals to entire right hand side is a constant. So what does it mean, guys? PV equals to constant. Now you tell me, is pressure constant? No. Is volume constant? No. What is constant? The product of
Product of pressure and
the
volume.
product of
Volume.
pressure and volume is a
Constant.
is a constant. Okay, you know what does it mean? It means that the product of P into V1, okay, pressure into volume at any time will be equal to pressure and volume product anytime later. I can just do it for any time I want. Okay, so let me just show you what do I mean by this. Okay, so let me show you again here. Okay, so don't forget, in an isothermal process you are always going to write what, guys? The product of pressure and volume must be a constant. Okay, how do we get it? PV equals to nRT. If temperature is constant, right hand side everything is a constant, so product of pressure into volume is constant. Okay, so when I go to this diagram, okay, let me just show you that I have done it for a particular temperature, so let me just show you that very quickly. Okay, now check. Okay, this is your volume, again same thing, I know, volume, and this is your pressure of a gas. PV indicator diagram, you can see this is volume V1, this is volume V2, this is pressure P1, this is pressure P2. Okay, so when the volume is V1, pressure is P1. So we have this point here. This is one of the state of the gas where the volume is V1, pressure is P1. Volume V2, pressure P2, somewhere here this much. Okay, so we have B state where we have volume V2, pressure P2. Okay, and I'm showing you the change. Look at this. You can understand this. Okay, so now you can see that the pressure is falling, but not very fast. I'll show you what is a very fast drop in pressure. Look at this. This is a very fast drop in pressure. Okay, the second one, the number 2 one, very quick drop in pressure. Okay, the pressure drops very fast. Okay, but don't worry, this will not happen in isothermal expansion. Okay, so when I have drawn this graph, I also should made it clear that the temperature right now is how much, guys? Let's call it T1 right now, some temperature called T1. Okay, so you tell me, guys. Okay, check, what is this? Will I call it volume in between V1 and V2, right? So let's just call it V3 right now. When the volume is V3, we also have a pressure, how much, guys? In between P1 and P2, that is how much?
P3.
P3. Okay, so at certain volume called V3, we have a pressure called P3. Okay, now I am going to ask you, okay, tell me, because I told you it is an isothermal process, what can I do? If it's an isothermal process, I can write the product of pressure and volume P1 V1 here. Okay, the product of pressure volume here is how much? P2 V2, and the product of pressure and volume is how much here? P3 and
P3,
V3. And we know, because it's an isothermal process, the product of these two must be same everywhere in the graph, not only here, not only here, not only here, but everywhere you want to do it, you can do it. Okay, but guys, are you clear with isothermal process?
Yes, sir.
Yes, sir.
Yes,
Okay.
sir.
Okay, so right now this is a gas at what temperature? Just check, because I need to make few more things to explain to you. I need to explain one or two more things. Are you clear with the temperature, guys? We're here with this process. Okay, T1. Okay, temperature is T1. Okay, now let's do the same thing. Okay, but I'm going to do this one. See, I'm going to take the, okay, Rikit is also clear with this. Okay, see, then check. Okay, if I write now P1, yeah, PV equals to N, R and T. Okay, Look at this and tell me, okay, if I start, okay, if I start with a higher temperature, just think about this. If I start with the same gas but at higher temperature, same gas at higher temperature, and I start with same volume, okay, just like this gas, okay, that we have V1, no, okay, so you think and tell me, okay, if I take a gas, the same gas like before that I have drawn the graph for, okay, but this time you know what I'm telling you, okay, I'm not starting with temperature T1, I'm starting with a temperature called T2. Can you understand what I'm trying to say, guys? But I start with same volume but greater temperature. What will you tell me about the pressure of this gas, guys? Will it be same or much
So
larger?
pressure will be more.
Yes, okay. Do you understand, guys, what I'm asking you? If I start with what, guys? Higher temperature, but if I start with same volume like the previous case, right, then automatically that is only possible if the pressure is what? High.
More.
Increasing.
Increasing, okay, the pressure should be high, okay, because of which you just check this graph now, okay, check, I'm going to just plot few more things, tell me whether it's making sense or not, okay, I'm just going to drop this part right now, look at my points now, okay, check, this is the point I've taken, now you think and tell me, what does it represent, guys? It represents the gas, yes. Does it represent the gas at volume V1? Yes. But why it is above this first graph, guys? Because it is same pressure or more pressure?
More pressure.
More pressure.
More pressure, and that can only happen if I'm taking the same temperature or higher temperature.
Higher
Higher
temperature.
temperature, okay, and the same gas, okay, now can again undergo expansion, okay, but this time it will fall like this, not going to go and meet the other gas, okay, because the first one, right, was entirely happening at what temperature? T1. Now what do you think, guys? This is temperature T1 or T2 temperature?
T2.
T2 temperature, which is much more greater than T1 temperature, okay. Now my question to you is this, okay, do you understand the difference between this graph and this graph, guys? Yes, Alishiba is asking something. Yes, Alishiba, you want to ask anything? Okay, okay. Then Alishiba is eating something, no? Okay, see, okay. Then what else, guys? Oh yeah. Do you understand, guys? When the temperature, when the curve is drawn here, when the graph is drawn above the other graph, right? What is your idea? The moment you see a graph on top of another graph, right? What does it mean for pressure volume graph? It shows that for the second graph, the above graph, right, the temperature must be greater than the first one, okay. So this is what we are talking about, okay. I think you're clear with this one. Is it okay? Can I say it's okay? So just by looking at the graph, we should be able to tell, no, which one is at higher temperature and which one is at a lower temperature, okay. Notice what can happen, okay, if I just not talk about expansion, if I talk about compression, okay. Compression means to come from a bigger volume and go to the smaller volume, okay. That means the graph should go to the left, okay. So when the graph goes to the left, this is what happens. I'll show you. Say, same kind of trend we are going to get, okay. Same kind of trend means exactly same states the gas can pass, but again one graph will be on top of the other graph, and again it indicates that this is a higher temperature and this is a lower temperature, okay. Basically what I'm trying to tell you is that this is compression, and when compression happens, right, in an isothermal condition, okay, what should happen, guys? The pressure should rise, but because the temperature is not increasing, no, the pressure also cannot rise very fast. So remember this, isothermal compression, the pressure will rise but not so fast. Isothermal expansion also, the pressure will fall but not so fast, and the temperature, they do not change, okay. This is all about your isothermal, okay. And one more thing, yeah, you can always use this equation for your isothermal, okay. Example, I can quickly come and give it to you. The examples is this, okay. Say boiling process. Tell me what happens, guys, during boiling process. Vinayak has joined so late. What happens in boiling process, guys? Okay, what is water? No, water and boiling. Tell me, guys.
The temperature remains constant.
Okay, what is boiling? But boiling means what? Liquid is going to become
Gas.
vapor, and this happens exactly what temperature?
100 degrees
Normally it happens at 100 degrees Celsius, okay. Yes, okay. So boiling is a process, right? You'll agree with me. Boiling is a process which happens at what temperature, guys?
100 degree
100 degree, you
centigrade.
agree with me? So temperature is constant, right, for this process? Yes, temperature is constant, and something is changing. What is changing? Liquid is becoming vapor. Do you agree with me? It is at expansion or not?
Yes,
Yes,
sir.
sir.
Okay, so this kind of expansion, right, happens at what temperature? At a different temperature or constant temperature?
Constant temperature.
Yeah, and that's why, okay, boiling is a process which is called what process? It's a what process?
Isothermal.
Isothermal
Isothermal.
process. Even melting, okay, melting takes place at what temperature, guys? Melting of ice, no? Melting, okay,
0
melting.
degree.
Melting also takes place 0 degree, okay. Your solid ice becomes liquid. At what temperature it happens? 0 degree Celsius. So your ice, which is solid, right, becomes liquid. Okay, so this is also a process of expansion, okay, and we can call it uh, isothermal process, okay. So I think you got the idea why we are calling like that, okay. Then, okay, I'm done with this also. I've talked about this, and this part I think you can just read yourself, okay. The one I was talking about, this graph basically means what, guys? Which temperature is highest here? For which graph? 1, 2 or 3?
33.
For
3.
3, right? That's what it indicates, okay. That's all about this graph, okay. I'm done talking about this. Now I think I can really go to your adiabatic change. Adiabatic change are very nice, okay. Maybe you'll understand the moment I start speaking, and then we'll check what kind of equations we need to write for adiabatic, okay. That will solve half of our problem, because next two topics are very important. See, okay, some of my friends are messaging. Okay, 1 second, okay, 1 second, they're calling me to play games. Okay, see, okay, so what is this adiabatic change? Okay, see, adiabatic change, right? Let's take the gas again, okay. See, you really have to think of it, then we can proceed. See, guys, this is a cylinder enclosing a gas again, okay, an ideal gas. PV equals to nRT, I can use it, no problem at all. PV equals to nRT. But now I'm not saying temperature is constant, okay, but I can use this anytime, anywhere I want, okay. So now check. Right now the volume of the gas is V1. Right now the pressure of the gas is P1. Right now the temperature of the gas is T1. This is one of the state of the gas. This is what we have right now, okay. Then, you know what, okay, adiabatic, the word adiabatic, okay, adiabatic simply means what, guys? Can heat enter or cannot enter, guys? Heat
Cannot enter.
is not allowed, cannot enter, not allowed to enter. Heat means energy cannot come from outside, okay. Now you think, if the piston, okay, goes from this position, okay, and reaches this position, tell me, the gases have pushed the piston or not? What do you think? If the piston has really gone from there to there, okay, from here to here, so now you tell me, okay, the gases have really pushed the piston or not?
Yes, sir.
Okay.
Yes, sir.
Yes,
Yeah, the
sir.
gases have pushed the piston. If the gases have pushed the piston, okay, do you agree, first of all, the volume will be same or increased?
Yes.
Increased, okay, agreed with that. Now, do you think the gases are pushing the piston? Yes, gases are pushing the piston. Did the gas get extra energy from outside, or they are using their own energy?
Using their
Using their own
Using their
energy.
own energy. No chance of getting help from outside, right? So using their own energy. What is the meaning of using their own energy? The internal energy remains the same, or internal energy decreases?
decreases.
Internal energy decreases. If
Decreases.
internal energy decreases, indirectly what does it mean, guys?
Temp.
Very good.
Temperature
The
decreases.
temperature should fall. Very good. The temperature should fall. And what is the meaning of temperature falls? The gases become fast or they become slow?
Slow.
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 So when the gases they become slow, what kind of pressure they will apply on the walls, guys? Pressure they'll be same or it will
Less.
decrease very quickly?
Very
Decrease.
quickly.
Decrease
Quickly.
very quickly. In the previous case, temperature did not change, okay, so gases could go and hit the walls, okay. And
So
the pressure,
temperature will fall at a higher speed, right?
let's not say highest speed but rate, no, at highest rate.
Okay.
Not, let's say highest rate is not the word we should use, but let's just say uh, the rate of which the temperature falls is very fast, okay. So that's why, you know what, the pressure, the decrease, right, the pressure is going to decrease very what, very fast, not like your isothermal process, okay. Because of which, check my graph now, okay, check. check the graph. Okay, see, you can easily understand how it should happen. Okay, check. This is what, guys, this is volume, this is pressure. PV indicator diagram again I'm drawing. So I start with a volume V1, I go to a volume called V2, I will start with a pressure called P1, but this time I'm going to get a pressure called P2, which is very, very low. Okay, check. So when I start with this much pressure and volume, right, V1, this one, and V2, right, yeah, so this will be till here, I think. Okay, so this is your second point, this is your P2 V2 or V2 P2, this is your P1 V1, the first state. Check how am I drawing the graph this time, guys. Look at the graph. Do you think it is decreasing like before? I just drew it like that. Okay, the pressure was decreasing, it was going down but not so fast, but now I'm showing you directly, right? Okay, you can understand the pressure falls very, very fast. So if I start here with a temperature called T1, guys, what will I get by the end of this process? Will I get the same temperature or lower temperature?
Lower temperature.
Lower temperature. And look at this, the pressure is falling. It's not a straight line, it's a curve. Okay, the pressure falls very, very quickly. Okay, actually I could just draw it like that also, huh? So let me just do that. Okay, so you can understand. Please tell me, guys, what will I call this process now? I'll call it expansion or adiabatic expansion? Adiabatic expansion. Okay, that means increase of volume of a gas and very quick rapid decrease of pressure without absorbing any heat from outside. Okay, so this is what we have. Okay, I think it makes sense. Okay, but look at this now. Can I use this equation PV equals to nRT? Yes, you can use. Can I use for the first case? Yes, I can use it. PV equals to what, guys? nR, what should I write here now? T1, right? Because in this position, right, the temperature is T1. Okay, at any other point somewhere here, guys. Okay, what do you think? The temperature is T1 or it is a different temperature? What do you think, guys, there? Different pressure, different volume, and even different temperature. Okay, as I keep on moving along this adiabatic curve, right, the temperature is going to keep on changing as well. Okay, even the pressure, volume, and temperature, all of them are changing. Okay, what will be the another equation I can write here, guys? What is that equation? I can write P2 V2 must be equal to what, guys? N into R into T2. Okay, this is I can use. Okay, but I cannot say this time that P1 V1 is equal to what? P2 V2. This is not correct. Okay, this doesn't happen. Okay, because temperature is right hand side is not a constant anymore, so I cannot do that. Okay, but these people, okay, they have a formula, okay, which I'm going to use now. Okay, but before that I need to ask you something. Okay, say, okay, you at least have understood, okay, that when the gas doesn't take heat or doesn't lose heat, right, and when it undergoes expansion, the pressure falls very, very quickly. Okay, what about the opposite, guys? So during compression, suppose I talk about compression. Compression means what? You take the gas in a piston, and this time what will happen? The gases are there, okay, and you know what? You take the piston and push the gases. Now the piston appears here now. So now all the gases will be occupying this much space, right? So now you tell me, guys, this is increase of volume or decrease of volume? This is decrease of volume. Okay, now you think and tell me. Okay, if you decrease the volume, okay, fine, the pressure, what do you think will happen? It has to increase. Okay, what kind of collisions you are going to get, guys? You're going to get collisions between the molecules or get more collisions?
More collisions.
More frequent collisions. More frequent collisions. More frequent collisions is going to generate what, guys?
More pressure.
Generate heat. Collisions, they generate what? Heat, no?
Heat.
Okay, collisions, they generate heat, and heat will make the temperature same or it will make the temperature go up?
Temperature will rise.
Okay, so temperature will rise. Okay, and what about the pressure, guys? What do you think? The pressure will rise or rise very quickly?
Very quickly.
I'll tell you why very quickly. Because do you think the gas will give any amount of heat outside or will not give any heat outside?
Won't give any heat outside.
Because it is adiabatic process. No, it will not gain heat also, and it will not lose heat also. That's why the pressure is going to rise very quickly. Okay, because okay, the gas is not giving out any heat outside. Okay, but if the gas was giving heat outside, guys, what will happen? The pressure will rise or rise slowly?
Rise slowly.
Okay, I hope you understand what do I mean to say by that. That's why you get same kind of graph, and you can just change the arrow, right, showing that it is what now, guys? It is compression, and the pressure is going to rise very quickly. Okay, so this is your PV indicator diagram. Okay, this should look like this for your adiabatic compression. Okay, and again I told you earlier, right, if I start with a bigger temperature, much bigger than T1, I can start the graph here, here and here. Okay, like that is going to happen. Okay, so I don't need to talk about that. But now very important point. Okay, see, you will also agree with me on this. Okay, just check. See, do you agree that different gases, okay, different gases, the pressure that will build upon them, right, will be different or not? The pressure, right? Imagine, okay, I can just show you very quickly. Imagine I take a container. You can imagine I take a container. Okay, I take a gas called gas number 1. Okay, let's say oxygen, and this is, let's say, hydrogen. Okay, and you know what, I started with same volume of both of them. I made them undergo adiabatic expansion. Okay, adiabatic expansion, both of them. Okay, both of them are expanding, so the piston is going to reach here, the piston is going to reach here. Now both of them, they are occupying more space. Okay, both of them are occupying more space. Do you agree with me that if here, right, what will happen? Pressure will fall or rise? Fall. Here also pressure will fall, but the amount by which the pressure will fall, okay, will it be same or it will not be same in both of them? First of all, is that
Not be same.
not be same? Okay, who will lose pressure fast? Can you just guess? I think it is going to be hydrogen, right? Because it has less mass, no? I think that is why I think pressure in hydrogen will decrease much faster. Okay, but that's a different case, don't worry about that. But my point is this. Okay, just think and tell me. Let me frame my question properly. The thing which I want to ask is the thing which I want to ask you is this. Okay, earlier I wrote this one, just check, PV equals to nRT. I can just write P equals to nRT by V. I can always use this, I told you, right? And again, it simply means what, guys? If the volume increases, the pressure has to fall.
Pressure decreases.
Pressure decreases. Okay, but this time let me just show you what happens. See, in adiabatic, okay, in adiabatic process, depending on the nature of the gas, the pressure will fall. But this time I cannot write like this. Okay, I cannot do this. This is not correct. This is correct for what? Correct for isothermal.
If nRT is constant.
Yeah, T is constant, so P is inversely proportional to what, guys? Volume to how much power? Power 1. Pressure to power 1 and volume to power 1. Okay, this is how pressure changes with volume if it is isothermal process. Okay, so look at the power of volume and look at the power of pressure. It is all 1 so it is quite fine. This one is fine. We got this equation. Everybody is okay with this. Okay, and you know how does it look like? Look at this. This looks like this. The pressure falls slowly. Okay, P1. Here the pressure is P2, but it falls very slowly. Okay, but today we are talking about this process. Look at this. The pressure falls very quickly, rapidly, right? So what do you think, guys? Is this correct or not correct for adiabatic?
So not correct.
Not correct. Why? Because yeah, when volume increases, okay, let me just write it down. When volume increases, pressure decreases or decreases much faster?
Much faster.
Much faster. That means the change of volume has effect on pressure, or very huge effect on pressure compared to
Huge
isothermal. Compared to
Huge
isothermal. Okay, I'm repeating again. Okay, in this adiabatic process that I'm talking about, okay, the increase of volume has a huge effect on the pressure. The pressure is going to fall very, very quickly. Okay, and that effect, okay, cannot be written, okay, we're using this this expression here. Okay, but it is written like this. See, it is written with V to the power gamma. I'll tell you what is gamma. Gamma is a complex issue right now. Okay, gamma is a ratio between Cp and Cv. Let me just define to you very quickly what is that. It is called specific heat of a gas at constant pressure, and this is divided by specific heat at constant. Don't worry about this right now. Okay, just remember there is a number called what, guys? Gamma, which is Cp by Cv, which depends on the gas. Okay, right now I'm just telling you this. See, guys, I told you that increase of volume has a huge effect on pressure. Okay, and that's why the power of the volume cannot be what? 1. In this case, the power is found to be equal to gamma in adiabatic process. Always remember this. Okay, that means, you know what, when I change the volume, okay, volume changes, no problem, but 1 by volume will change to the power what? Gamma, and as a result the pressure can decrease now very rapidly. If I just put here V, it doesn't decrease rapidly. That doesn't indicate mathematically that it decreases rapidly, okay? But if I have volume to the power gamma, now it indicates what, guys? Now it indicates what, guys? That yes guys. Oh, by the way, I should write gamma is greater than 1, okay? Always remember this. This is a small information about gamma, this one I will talk later, not possible right now, okay? Talk later about this one. So guys, I just want to ask you very quickly, okay? Tell me, in adiabatic process also pressure depends directly or inversely on volume? Adiabatic, just tell me this.
Inversely.
You'll get your answer, okay? Adiabatic also, when the volume increases, pressure decreases. But does the pressure decreases or decreases very rapidly?
Very rapidly.
That means the change of volume has a huge effect on what? Pressure. So should I write a power 1 or power should be more than 1, guys? Here the power
More than
1, and it depends on the gas, okay? And that's why we're writing a property of a gas. We call it gamma. And what is gamma, guys? We call it ratio
CP.
of Cp by Cv. For the time being, only this much information, okay? Because of this power gamma, okay, you are obviously going to get a graph which looks like this every time. See, a very quick drop of pressure or very quick increase of pressure when we change the volume, okay? So this is what I've been writing all around, okay? So I'm going to write again. See, so when I go back, okay, I'm going to write again. So P is inversely dependent on what, guys? Now we learn is volume to the power gamma, or I can also write here equals to, okay, P equals to constant divided by volume to the power gamma. Same expression you can check for adiabatic, or I can write PV to the power gamma is a what? Is a constant. So always remember this. This is what you are going to use for all the time. What process, guys? Adiabatic processes, okay? Please remember this, okay? So yeah, can you just apply it to different state A and B? How will I apply now? I'll write here P1 V1 to the power gamma must be equal to what? P2 V2 to the power gamma, or I can apply to any other state P3 V3 to the power gamma. That means at different locations on the graph, right? I can apply this, okay, but taking different volume. But don't worry, you don't have gamma 1, gamma 2, gamma 3, okay? You have only one value of gamma, okay? You don't have gamma 1, gamma 2 and gamma 3, okay? Yeah, is it clear, guys? Just check. Can I say it's clear? Little bit at least.
Yes, sir.
So what is constant in adiabatic process? Pressure into volume to the power gamma is found to be constant, okay? This is what you need to remember. Please remember this, okay? Then examples I gave you last time, please read it, okay? I hope so it is clear, okay? Then this one I showed you just now for adiabatic. Remember, this is what we have to use, where gamma I told you is this. For the timing, just use directly, okay? But now I can make this expression, okay? Look at this. PV to the power gamma is a constant. I can just write in different ways, okay? This is not the only way to write for adiabatic, okay? I can write in different ways. Let me just show you. See, first of all, what I will be doing is, in place of P, because I always can use this one, right? PV equals to nRT, PV equals to nRT. Let me just show you all of them, okay? Let me show you one by one. See, let me go back here. Then we'll stop for today, okay? 1 hour class, so that you guys don't get bored, okay? See, PV to the power gamma, I told you, is a constant, okay, which means I can write P1 V1 to the power gamma must be equal to P2 V2 to the power gamma. We'll do numericals also, you have to do today based on this question, say. Then yeah, this is fine. This is what you can do. The next thing you can do is this. See, guys, for 1 mole of a gas, okay, 1 mole of a gas, of an ideal gas, what is the meaning of 1 mole, guys? N equals to 1. This one is clear. 1 mole of a gas, no, you take, then you can use this, no? Then check, okay? For 1 mole of a gas, tell me, what can I write? Ideal gas equation. PV equals to nRT, right? Will be written as PV equals to just RT. So in place of P, what can I write in this equation, guys? RT by V. Okay. By the way, let me ask you again. Can I use this or not? This one. Can I use this or not?
Yes, sir.
Let it be adiabatic, I told you. Let it be adiabatic or isothermal process. I can use this. Okay. So allowed. Okay. From here only I'm getting this expression, which I can substitute for your P. So I'm going to do that right now. Okay. So let's just go back here now. See, I'll go back here for an adiabatic process. and I told you this is not the only way we can write. Okay, so let me just use it over there. Please tell me guys, what will I get? In place of P, I'm going to write RT by V,
V.
and then I have V here to the power gamma equals to what?
Constant.
Constant. Okay, I can do that.
Constant.
Then T, then V to the power how much guys? Does it look gamma or gamma minus 1 now?
Gamma minus 1.
Because when this volume goes up, it becomes negative 1 power. Okay, and that R, I'll show you where it is. Okay, that R is below this constant. Now say take a constant, divide by that R. Okay, so what is this? Everything is again a
Constant.
because a constant divided by universal gas constant, right, is going to be a constant. So I'm not worried about R. Okay, so it's going to be a constant. So this I'm simply going to write a constant. Okay, so what did you learn just now, guys? Check. Is this the only thing that we need to write for your adiabatic, or I can write this also? I can write this also. So what is this also represents? It also represents adiabatic process. TV to the power gamma is constant. Now can I apply, guys? How to apply? Tell me. T1 V1 gamma minus 1 can be written equal to what?
T2 V2 gamma minus 1.
Gamma minus 1. For an adiabatic process only you can do this one. Okay, so I have one more substitution. Okay, just check whether it makes sense or not. So you got two formulas already. This is the one for an adiabatic process, this is another one for an adiabatic process. I need to show you one more. Okay, check. And that is very simple again. Say in place of P equals to RT, right, let's write V now. Okay, V equals to what, guys? I can write RT by P. Okay, I'm going to come back and substitute it there. Okay, so tell me, what do I get? P, waiting. In place of V, I'll write RT by
RT by P.
but this time I'll write to the power gamma equals to a constant. Okay, so now tell me, what do I write, guys? P
RT gamma.
RT R gamma, right? T to the power also gamma by P to the power
Gamma.
also gamma. So this is going to look like how, guys? P to the power what?
1 minus gamma.
1 minus gamma, and T to the power gamma must be equal to what? Must be equal to a constant divided by R to the power gamma, and we know this is again a what?
Constant.
Again a constant. So I can write this also. So what is this? P to the power 1 minus gamma T to the power gamma can be written is equal to what, guys? This is also I can use. Okay, and there are many other ways also you can just use them. Okay, so this is one of them. See, another one of them. Okay, so all these things are in the notes, please go through. So I think it should be fine. Okay, oh yeah, very quickly let's check. Okay, I think you agree with this. What is this, guys? Will I call it expansion or not? Check. Both of them are what? Expansion or compression? Expansion. Okay, do you understand this one represents a quick drop in pressure, slow drop in pressure? This one
Slow drop.
So it is what process?
Isothermal.
Isothermal. And this is
Isothermal.
quick drop in pressure. So what is this? Adiabatic. Okay, yes, let's come back here. What is this, guys? Expansion or compression? Both of them.
Compression.
Compression.
Okay, what does it indicate? Increase of pressure or quick increase of pressure?
Quick increase.
That means without losing heat. Okay, so it is just getting compressed. So it is what process?
Adiabatic.
Very
Adiabatic.
quick increase in pressure. Okay, and this one is isothermal. What is that? Isothermal compression. Okay, so I think till now you guys are fine. Okay, so yeah, now I think I'm not going to do the other topic right now. Okay, the other two topics, that is work done in isothermal expansion, next time we have to do it. These two topics we'll do next time together. Okay, I will teach you nicely that one, but now I think I have to give you numerical. Okay, you really have to do this one. I saw it somewhere. Let me just find it out. Where is it? Right? Okay, I'll do like this. I'll search it and I'll send you in the group. Can you do it, guys? When I send you in the group, can you do it? Will you
Okay,
do
sir.
it? Will you do it?
Okay, sir.
Okay. That is an NCRT problem, maybe. Okay, no, those type of questions they used to ask. Okay, in the exam, huh? So I'm going to send you. So I think I can stop for today, no? Guys, so that you guys also don't get bored. Okay, that's why I'm taking 1 more hour class. Many students, so they have left the tuition. No, some of them. Okay, from Elishiba's batch to many of them, they have left the tuition, right? From army school, not army school. What school? BSS school, right? And other students from Anthony's also are not showing up, right? These people. Let me count out. Let me name them. Right? Who are they? See. Let me check who used to come, who don't used to come. Bajirihun used to come. Aisha used to come. Ankit used to come. Okay, let me stop recording.